It's chemistry and you are watching Chem Science.
In this video, let's discuss the latest paper of A-Levels question paper 4-2 of the 9701 chemistry of the examination series Feb March 24. So let's start without wasting time of the question 1. And here is question 1, which says potassium iodide Ki is used as a reagent in both inorganic and organic chemistry. Now Ki forms an ionic lattice that is soluble in water. So Ki is an ionic solid which is soluble in water, and the sub-question 1 says define enthalpy change of solution, that is delta H solution. So what is enthalpy change of solution? It is the enthalpy change when 1 mole of a substance, I'm writing a substance, but you can even write 1 mole of an ionic solid also. 1 mole of a substance dissolves in sufficient water. It's necessary to write sufficient water because we are not going to make a concentrated solution. So dissolves in a sufficient water to form infinite dilute solution. So energy change involved with this process is called enthalpy change of solution. Now let's go ahead with the sub-question 2. It says Ki has a high solubility in water, although its enthalpy change of solution is endothermic. Explain how this high solubility is possible. Now the thing is that enthalpy change of solution has to be exothermic for a substance to be soluble. But here the enthalpy change of the solution is endothermic and still the solubility is very high. Now how is that possible? Now this is possible only when the delta S, that is entropy change is positive with a large value, and this makes delta G negative, and if the delta G is negative for any process, then that process or the reaction is feasible. So here the process becomes feasible, that the process of being soluble becomes possible, and that's how, even though the enthalpy change is endothermic, the solubility is very high. Now if you look at the table 1.1, it gives some data about the halide ions, that is chloride, bromide and iodide, and their potassium salts. Now the halide ions are given, and the potassium salts of these halide ions data is given here. It says the enthalpy change of hydration of potassium chloride is given here. Enthalpy change of lattice energy of potassium halides are also given here. Now explain the trend in the enthalpy change of hydration of the halide ions. Hydration means this way. If you go look at the value, it's going less negative. So first let's write the trend. What's the trend? That enthalpy change of hydration, that is delta H hydration, becomes less negative, or you can even write that it becomes less exothermic. That is also possible. So delta H hydration becomes less negative. Now how? Explain means give reason. So whenever you come across this term explain, that shows that you need to give the reason. So if we give the reason here, says that less negative, that becomes less exothermic, that shows that the less energy is released out. Now if the less energy is released out, that shows that there must be some reason. The reason is that if we go down the group, the anionic size increases. Now anionic size increases, so let's write because the anion size increases. If anion size increases, in place of that you can even write that the charge density decreases. Now it means the same. Now if the anion size increases, the attraction the attraction between the ion and the water molecule decreases, and if the attraction is less, the energy released will also be less. So that's how the enthalpy change of hydration becomes less exothermic. Now before writing this answer, you should also understand what exactly is enthalpy change of hydration. Suppose there is an anion, that is chloride ion here, and when this ion gets surrounded by water molecule, then the energy involved is called enthalpy change of hydration. Now if this is a negative ion, then the partial positive hydrogen gets attracted to the negative ion, and this is how the hydration enthalpy arises. Now if this anion size is bigger, the attraction between this partial positive and the anion is less exothermic, or the attraction force is less, you can say, and that's how the energy becomes less exothermic. Now let's go ahead with the next sub question. It says enthalpy change of solution values for this potassium halides are almost constant. Use the hydration and lattice data in the table 1.1 to suggest why. Now if you talk about enthalpy change of solution, that is enthalpy change of hydration minus lattice energy. Now if you look at the data, hydration is getting less exothermic, lattice is also getting less exothermic as the anion size increasing, and if you look at the change, it's almost constant for both the values, that is hydration and lattice energy, and that's why the change in the energy, that is enthalpy change of solution, that is hydration minus lattice, is almost constant. So it's just 1 mark, so you can just write one sentence that hydration and lattice decreases by similar values, or you can say that the difference between the hydration and lattice is almost remaining constant going down the group. You can write it in any ways. I'll just write that enthalpy change of hydration and enthalpy change of lattice becomes less exothermic. Both of them are getting less exothermic because the negative value is decreasing, so becomes less exothermic. I think I made a mistake in the spelling. Exothermic by similar values, and that's how the enthalpy change of solution remains almost constant. Let's go ahead with the next sub question. It says enthalpy change of solution of Ki is plus 21.0 kilojoules per mole. Now this is the value of solution given here. Use this information and the data in the table 1.1 to calculate the enthalpy change of hydration of potassium ions. So if we write hydration is equal to, you can say that lattice plus solution. Okay, now hydration is the hydration of both Ki, both potassium ion, and hydration of iodide ion. Now if you are supposed to calculate the value of potassium ion, then the iodide ion's values is already given, and that we need to find out. Yes, potassium we need to find out, and iodide is given, and the lattice and the solution should also be given. Now solution is given here, you can directly substitute, that is plus 21.0. Now if we talk about lattice, let's find out about the potassium iodide lattice. Yeah, potassium iodide lattice is minus 629 kilojoules per mole. So minus 629 kilojoules per mole. So I am writing 21.0 here. And yes, the value of Ki also moves on the other side. So here should be the hydration value of iodide ion. So hydration value of iodide ion is minus 293. So minus 293 has to be added here. So minus 293. So this is how you're going to write. So what have I done is that hydration is the some values of the hydration of potassium ion and the hydration of iodide ions. So I have removed the hydration ion and moved it on the other side of the equation, and that's how the hydration of iodide is on the other side. Here I have substituted the lattice, here I have substituted the value of solution, and this is how we calculate the hydration value of potassium ion, and this sums up to minus 350 kilojoules per mole. Now the value is given, so I'm not writing it here. Minus 315.0 kilojoules per mole. So this is how we calculated the hydration of potassium ions. Solid lead iodide, this is lead iodide, forms when potassium iodide is mixed with the lead ions, aqueous. The solubility product of KSP of potassium iodide, not the potassium iodide, again it's lead iodide, is 7.1 into 10 power minus 9, value at 25 degrees Celsius. Calculate the solubility in moles per dm cube of lead iodide. Now how do I teach my student is that first you need to write an equation where potassium iodide is splitting up into the ion. So this is how you get the value. Now if this is how you get the value of solubility product, then if the solubility is X, then the solubility of solubility of lead ion is also X, but the solubility of iodide should be 2X. Okay, so if you now make a expression for solubility product, then it should be the concentration of lead ions into the product of the concentration of iodide ions raised to the power 2 because of the stoichiometry of 2. Now if you substitute the values here, it should be X and 2x squared. This is how it works, and the solubility product value is given here, that is 7.1 into 10 power minus 9. And if you get the value of X, that's how you get the value of the solubility. And if you simplify it, then it's going to be 4x cube. So if you find out X value, it has to be the cube root of 7.1 into 10 power minus 9 divided by 4, and this is how you get the value of solubility, which is 1.21 into 10 power minus 3. So this is how we get the value of solubility of lead iodide. Fifth sub-question says the ionic radius of lead ion is 0.120 nanometer compared to 0.133 nanometer of potassium ion. Suggest how the value of lattice of lead iodide differs from the lattice of the potassium iodide, and explain your answer. If you now look at the ionic radius of lead, it is 0.12 and 0.13. So you can say that the lead ion is smaller in size compared to the potassium ion. So you can explain here that as the lead ion is smaller, the attractional force between lead ion and iodide ion is greater, and so the value of lattice energy of lead iodide is more exothermic in the sense it will be a more negative value because of the smaller ionic size. The attraction force between the two ions is greater, and hence the lattice energy is more exothermic. This is how you're going to explain for the 2 marks. That is, the first point is very necessary, that the lead ion is smaller, or you can say the charge density of lead ion is higher, and that's how the attractional force between the two ions is greater, and explain your answer. So you also have to suggest the difference. The difference is that the lead ion is more exothermic, or you can even write that the lattice value is more negative, that is also acceptable. Now let's go ahead with the next sub question. Here it says C, Ki slowly oxidize in air forming iodine molecules. So here is the equation given where the delta H, that is the enthalpy change, is minus 203.4 kilojoules per mole. Now what's happening here is that potassium iodide is getting oxidized in air, reacting with the oxygen and carbon dioxide, where iodine is formed in the form of a solid. Here it's solid. The data relevant is given in the question. So here are the values of entropy of each of these substances. Calculate the standard entropy change delta S for the reaction 1. Now standard entropy change is what? Product minus reactant. So what is the products? Potassium carbonate and iodine both have a mole ratio of 2 each. So delta S is equal to 2 into 155.5, which is the value of potassium carbonate, plus 2 into the iodine value, that is 116.1. Now that is the product side, minus the reactant side. Now if you have a look at the reactant side, it is potassium iodide, carbon dioxide and oxygen with the ratio of 4:2:1. So we need to substitute all these values. So in that case, 4 multiplied by the potassium iodide value, that is 106.3, plus 2 into the value of carbon dioxide, that is 213.6, plus the value of oxygen, which is 205.2, and that is the reactant side done. So product minus reactant, which is minus 514.4 kilojoules per mole. Yes, sorry, the unit of entropy is joules per Kelvin per mole. So this is how you're going to calculate the entropy change of a reaction, that is product minus reactant. So let me substitute here 514.4 joules per Kelvin per mole. Use your answer to C1 to show that the reaction is spontaneous at 298 Kelvin. So the temperature is given, delta S we have calculated, and if you have a look at the reaction, the delta H value is also given. We need to substitute all these values to calculate delta G, that is Gibbs free energy, and the equation for this is delta H minus T delta S. If you substitute the value of enthalpy change, what it was minus 203.4. So minus 203.4, but that was in kilojoules, which we need to convert into joules. So 10 power 3 minus temperature, that is 298 Kelvin, into delta S value, which is minus 414.4. So this is how you're going to calculate the delta G value, which is 50108.8 joules per mole. If we want to write it in kilojoules per mole, we can still write it as 550.1 kilojoules per mole. This is how also we can write, or we can write it the way it is joules per mole. That is also acceptable. The next sub question says the group 1 carbonates are much more thermally stable than the group 2 carbonates. State and explain the trend in the thermal stability of group 2 carbonates. Now that's a fixed answer, and I'll always tell my students that some fixed answers you should just learn. So starting with the trend, we says that the thermal stability of group 2 carbonates increases down the group, increases down the group, and the reason for that is down the group because the cation size increases, because of that the ion polarization decreases. As the cation size increases, polarization decreases. So the ion polarization decreases, and this makes the and this makes the CO bond stronger, which needs high energy to break down, high energy or high heat energy you can write, to break down, and that's why the thermal stability increases down the group. So this is how you're going to write. You can even make it shorter because it's just 2 marks. Now let's go ahead with the next sub question D. It says a student electrolyzes a solution of Ki aqueous, that is potassium iodide, for 8 minutes using a direct current. Now the half equation for the reaction that occurs at the anode is given. At the anode, the iodide ions are oxidized to iodine in aqueous form and the 2 electrons are released. Now the sub question 1 says write an half equation for the reaction that occurs at the cathode and include the state symbols. Now the first thing is which ion is discharged at cathode. Now if you look at the aqueous solution of potassium, the ions which are present are potassium iodide, hydrogen and hydroxide. Out of the 2 cations at cathode, the one which is less reactive, that is hydrogen, will be released. The one which is more reactive, potassium, does not get discharged. So at cathode, hydrogen ion gets released, forming hydrogen gas. Now if you'll have a look, we need to balance the hydrogen ion by 2 because there are 2 hydrogen atoms combining to form the hydrogen gas. So to reduce it, we need 2 electrons to form the hydrogen gas. So this is the half equation at the cathode. Now they've written include the state symbols. So obviously we need to write aqueous here because the hydrogen ions comes from the water, so it's aqueous. Now sub question 2 says after the electrolysis, the iodine produced requires 21.35 centimeter cube of 0.1 mole per dm cube Na2S2O3, that is sodium thiosulfate, to react completely, and this is the equation given. Calculate the average current in 8 minutes during the electrolysis. The first thing is that we need to find out the moles of iodine, and to find the moles of iodine we can use the moles of sodium thiosulfate which are given here, but we can see that the ratio of iodine and sodium thiosulfate is 1:2. So sodium thiosulfate volume and concentration is given here, that is 21.35 into 10 power minus 3, because we change cm cube, centimeter cube, into dm cube, into the concentration, that is 0.1. So this is how we find the moles of sodium thiosulfate. But to find iodine moles, we need to divide it by 2 because of the ratio of 1:2. So 21.35 into 10 power minus 3 into 0.1, that is the concentration, divided by 2, which is equal to 1.07 into 10 power minus 3 moles of iodine. Now let's have a look at the half equation of iodine. Now we can see that to produce 1 mole of iodine, 2 moles of electrons are passed through the circuit. So if we check, to produce 1 mole of iodine, we need 96500 into 2 moles of into 2 coulombs. This is the rule where 1 mole of iodine is produced by 2 moles of electrons. So 9650 into 2. Why? Because 96500 is the charge where required to, when 1 mole of electrons or 1 mole of singly charged particles are passed through the circuit. So here if 2 moles of electrons are passed, then we need 96500 into 2. And now if we have 1.07 into 10 power minus 3 moles of iodine, then how much of the charge is required? That is how we are going to find it. So charge is equal to 1.07 into 10 power minus 3 multiplied by 96500 into 2. Now this is equal to 206.10 coulomb. Now this is the coulomb we have already known, and what are we supposed to find is calculate the average current. Now if we have the formula Q is equal to IT, then I is equal to Q divided by T. So if we have Q 206 0.10 divided by the time. Now if we check the time is 8 minutes, which we need to change into seconds by multiplying it by 60, which gives us the answer of 0.429 ampere current. So this is how we are going to calculate the current for any given process. Yes, the next question says potassium iodide is used as a source of iodide ions in organic synthesis also, and one of the example of this is shown here in the synthetic route figure 1.1. and here you can see that there is a benzene ring where the nitro compound is added, and this is the whole cycle where at the end an iodine is added. Now let's see what happens next is identify the reagents required for step 1 and 2. If we have a look at step 1 and 2, what is the first step? 1 is the nitro group is added to the benzene, and in the step 2 that nitro group is changed to the amine group, that is phenylamine. So for step 1 the reagents required are concentrated nitric acid and concentrated sulfuric acid also. Both should be concentrated, and it should be mentioned here separately because both the acid, sulfuric acid is concentrated, is used as a catalyst, and concentrated nitric acid is the main reagent. Both of it should be concentrated. In the second step, the nitro group is reduced to amine group, and for that we require tin plus again concentrated HCl. Concentrated has to be mentioned here, and this is how the nitro group is reduced to amine group. Let's go ahead with the next question. It says step 3 occurs in 2 stages. Sodium nitrate and HCl undergoes an acid-base reaction to produce nitrous acid, that is HNO2, and nitrous acid HNO2 reacts with C, that is phenylamine, to produce D. Now this is a diazo compound. Complete the equation to stage 1 and for stage 2, NaNO2 plus HCl. Now it's already written that in step 1 nitrous acid is produced, so HNO2 is definitely produced, and you can see that the remaining elements are sodium and chlorine. That's going to produce sodium chloride. In the step 2 it says nitrous acid reacts with the phenylamine, so HNO2 nitrous acid plus C6H5NH2, that is phenylamine. Now that reacts definitely, but in presence of an acid that is required. That's why this is the reaction where we need to include the hydrogen ion also, and that's going to produce the diazo compound, that is C6H5N2 plus, C6H5N2 plus. Now other than that, the byproduct is going to be the water molecule, and if you balance the reaction we need 2 moles of water is produced here, and this is how the equation is getting completed. Let's read the next part. It says iodide ions from Ki reacts with D in step 4. D is the diazo compound, and the mechanism is shown in figure 1.1. Suggests the name of this mechanism. Let's have a look at step 4. What is happening in step 4? We can see that the diazo compound N2 is attached to the benzene, and in its place the iodine comes in. So you can see that diazone N2 plus is replaced by iodide ions, and here you can see that the incoming group is negatively charged, that is a nucleophile. So the type of reaction you can say here is a nucleophilic substitution reaction. It is nucleophilic substitution reaction. The mechanism is named as nucleophilic substitution mechanism or reaction. Let's see what comes the next. Now it starts with the question 2. Question 1 is over, and here it starts with water is an amphoteric compound that also acts as a good solvent of polar and ionic compounds. Equation 1 shows water as a bronzed lauric acid. The equation is given here. Water reacts with the nitro group to form HNO2 and OH minus. Now identify the 2 conjugate acid base pairs in equation 1. Now here if acid 1 is H2O, if H2O is acting as an acid, it's going to donate its hydrogen ion. After donating the hydrogen ion, it's going to form OH minus, that is the hydroxide ion. So for the acid 1, the conjugate base is going to be the OH minus, and the acid 2, on the product side you can see that HNO2 is the acid 2, HNO2 is the acid. HNO2 is the acid and its conjugate base. Now after donating hydrogen ion, it forms NO2 minus on the reverse side. So NO2 minus is going to be its conjugate base. So this is how you're going to form the conjugate acid base pair from the equation given. This next sub question is, water also behaves as a bronzed-Lowry acid when it dissolves in the CH3NH2. Now this is methylamine. Explain the ability of the methylamine to act as a base. Now it says that water also behaves as a bronzed-Lowry acid when it dissolves with methylamine. So if you talk about water acting as an acid with the methylamine, we need to first write the equation about this dissolving in water. So what actually happens here is that the hydrogen of the water is donated and that is bonded to the NH3 plus, that is it gets bonded to the nitrogen's lone pair. A dative bond is formed with the nitrogen lone pair and that gets bonded with the hydrogen ion. So this is how it acts. So how are you going to explain it? Let's write it, the explanation, because here it says explain the ability of the methylamine to act as a base. So we can write here is that the lone pair of nitrogen is donated to hydrogen ion to form a dative bond, and this is how the nitrogen accepts the hydrogen ion, and that's why it acts as an bronzed-Lowry base, because that's the definition of a base, a capacity to accept the proton, that is accept the hydrogen ion. Let's read the next part. It says write an equation to show water acting as a base with the acetic acid, that is ethanoic acid. Now if water is acting as a base and we need to write an equation, so let's start by writing an equation, that is two reactants I've already written. Now if water is acting as a base, it's going to accept the hydrogen ion from the acid. So if it accepts the hydrogen ion from the acid, it's going to form H3O plus because it accepted the hydrogen ion. So water has accepted hydrogen ion to forming the hydronium ion called H3O plus, and the remaining anion left is the ethanoate ion, that is CH3COO minus, and this is how the equation is formed. Let's see what's the next part of the question. It says the ionic product of water Kw measures the extent to which water dissociates, and here it's written in the equation form. Figure 2.1 shows how Kw varies with the temperature. Now we can clearly see that at the temperature increases, the Kw value increases. So write an expression of Kw. Now expression of Kw can be written as the product of the hydrogen ion concentration with the concentration of hydroxide ion. This is how we are going to write the expression for the Kw. Use this information from figure 2.1 to deduce whether the dissociation of water is an exothermic or endothermic. Now if we talk about a reversible reaction, here is a reversible reaction because there is a reversible sign, and with the temperature, if the Kw value increases, that is the dissociation increases, then the reaction should be endothermic. Why? Because increasing the temperature, it favors the product side only when the product side, that is right hand side, is an endothermic reaction. So here we write it is an endothermic reaction, because with increase in temperature, Kw value increases. Now why does the Kw value increases? Because that is the dissociation of water into H plus and OH minus increases. Now as you can see, it's just 1 mark. So even if you write it's an endothermic reaction, because as temperature increases, Kw value increases, that also you can write because it just carries 1 mark. So 1 point explanation is needed. The next question is, an aqueous solution of pH is equal, an aqueous solution has a pH is equal to 7 at 30 degrees Celsius. Now use information from figure 2.1 to explain why this solution can be considered to be alkaline at 30 degrees Celsius. Now if we are talking about this solution at 30 degrees Celsius, let's see at 30 degrees Celsius what is the Kw value. The Kw value, you can say that here it is 1.50. 1.50 is the Kw value. Now if Kw value is 1.50, it's not exactly as 1.00 into 10 power minus 14 as the Kw value increases. So you can say that the pH of the neutral solution decreases. Now let's find out how it happens. Let's first calculate the Kw value. Kw we can write as H plus ion concentration square. Now Kw value is 1.50 into 10 power minus 14, right? It should be actually, for a neutral solution with pH 7, it should be 1.00 into 10 power minus 14, but now it is 1.50 into 10 power minus 14. So the hydrogen ion concentration is equal to the, or let's calculate the pH directly. pH is equal to minus log of H plus. So if we substitute the value directly here, we can write as half into minus log of H plus, that is 1.50 into 10 power minus 14. Now let's understand, this is a multiplication sign. It's not half minus, it's half into minus log of 1.50 into 10 power minus 14. Why? Because H square is here the root. If we find out the H plus concentration, let me write here to explain you. H plus is equal to the root of 1.50 into 10 power minus 14. So minus log of H plus can be written here like this. So pH is equal to, now this is equal to 6.91. So if you can say that the neutral solution is not having the pH of 7, but it is having the pH of 6.91 at 30 degrees Celsius. So at 30 degrees Celsius, if the neutral solution should have a pH of 6.91, then above 6.91 the solution becomes alkaline, and that's why we can say that the solution can be considered as alkaline at 30 degrees Celsius. So we can write in explanation that the pH of the neutral solution, pH of the neutral solution is 6.91, and so above 6.91 pH, the solution can be considered, alkaline. This is how we are going to write the explanation. It's just 2 marks, so 1 mark calculation and 1 mark if you show just the written work, it's fine. If we go ahead with the next part, it says the 3 physical states of water have a different standard entropies associated with them. Table 2.1 shows these entropy values. So here solid, liquid, gas entropy values for water, that is in different forms, is given here. Explain the difference in the entropy values of water in solid form and water in liquid form. Now as we know that the liquid has more entropy than the solid form, and the reason is that the randomness of the particles increases in the liquid compared to solid. So here we can write the same thing, is that the randomness or the disorder, the randomness or the disorder of the particles, or even you can write molecules, particles of water increases in liquid form, compared to compared to solid. So this is how you can explain about any common substances, not only about the water, but even if any substance melts, the entropy increases because the randomness or the arrangement of the particles, the ways of arrangement of particles increases. That is how also you can write that the ways of arrangement of particles increases in the liquids, so the entropy increases. Now it says next part, explain why increase in entropy is much greater than when water boils than when it is melting. And the only reason is that the disorder of particles increases much more in water in gaseous form compared to water in liquid form, and that is why the entropy of water increases much more when it boils and compared to when it melts. The next part, the energy changes of water solid to water liquid are shown here. The this is Gibbs free energy change is 0.00 kilojoules per mole, and the delta H, that is enthalpy change, is plus 6.03 kilojoules per mole. Now use this data to show that the melting point of water is 0 degrees Celsius. So let's start by writing just an equation, that is delta G is equal to delta H minus T delta S, all in standard form. Now delta G is given here, that is 0.00 is equal to the enthalpy change, that is 6.03 kilojoules per mole minus T into entropy change. Now let's see what is an entropy change when solid is changing to liquid. Now solid is changing to liquid. Now that is the entropy of solid at 48 and liquid is at 70.1. So we need to subtract 70.1 minus 48.0, which is equal to 22.1. So entropy change we can substitute here as 22.1. But then 22.1 you can say that it's only joules per Kelvin per mole, and here we are using the values in kilojoules, so we need to convert 22.1 into kilojoules. So we are going to write 22.1 into 10 power minus 3 kilojoules per Kelvin per mole. Now if you calculate the value of T, we can simplify and write it as T is equal to 6.03 divided by 22.1 into 10 power minus 3. That is equal to 272.8585 Kelvin. Now if it is almost equal to 273 Kelvin, that is 0 degrees Celsius. So you can write that 273 Kelvin is equal to 0 degrees Celsius, and hence prove that the water's melting point is 0 degrees Celsius. Let's go ahead. The next part, it says that metal air batteries are electrochemical cells that generate electrical energy from the reaction of metal anodes with air. The standard electrode potentials for the zinc air batteries are shown here, and here is the two reactions given in the reduction form. Now obviously when we know that the reaction is happening, one of it should be in the oxidized form and the other should be in the reduction form. Okay, so if we think about the zinc air battery, that shows that the zinc is the reactant and the oxygen, that is air, is the reactant. So in that case the first reaction has to be reversed. So in that case, when we reverse a reaction, that this reaction is an oxidized reaction. In that case the electrons are released, and in the second reaction the electrons are used up, that is in the reduction form. So because of that, the first reaction's electrode potential has to be reversed. That is, if it's minus 1.22, we need to use plus 1.22, that is positive 1.22, and then add both the electrode potential values to get the overall cell value. So here if we write it in the equation form, we'll write it as plus 1.22 plus 0.40. This is how we are going to write, that is we reverse the electrode potential value of the first reaction because it went reversed, because the reaction happened in the oxidized form. Okay, so because of that, the electrode potential value of the cell is 1.62 voltage. So this is how we calculate. Now the second part is the zinc air battery usually operates at pH 11 at 298 Kelvin, and overall the cell potential depends on the concentration of OH minus. Now the Nernst equation shows how the electrode potential at the cathode changes with the concentration of hydroxide ion, and here is the given value that electrode potential is 0.40 minus 0.059 upon Z into log of hydroxide ion concentration square, it's written. Now to calculate the value of E, we need to know the concentration of hydroxide ion, and to find out that, let's first use the pH 11 to find out the concentration of hydroxide ion. And now we know that Kw, that is ionic product of water, can be written as the product of the concentration of hydrogen ion and the concentration of hydroxide ion. Now Kw value is 1 into 10 power minus 14 and pH is 11. So from that pH 11 we can find out the concentration of hydrogen ion, that is 10 to the power of minus 11. That's how we write. So I'm substituting it directly here as 10 to the power minus 11 into the concentration of hydroxide ion, and in that case the concentration of hydroxide ion can be written as 10 power minus 14 upon 10 power minus 11, that ends up as 10 power minus 3. Now if we substitute the hydroxide ion value in the equation of E, we get 0.40 minus 0.059 divided by 2. Now why 2? Because Z is the value of the number of electrons we are using in the hydroxide ion equation, and that is 2 electrons we are using. So if we are using 2 electrons, Z becomes 2 into the log of the concentration of hydroxide ion square. So what's the concentration of hydroxide ion? 10 to the power of minus 3 square. Now if you substitute the whole value and calculate, we get plus 0.577 volts. So here we write the value 0.577 volt, and this is how we calculate the new electrode potential value of the hydroxide ion cell. Earlier the electrode potential value was the standard electrode potential value, okay, and here the values have changed, the standard conditions have changed, and because of that the new E value we have calculated with the help of Nernst equation. Now here question 2 ends. I hope question 1 and question 2 are very clear. It's very clearly explained, so I hope everyone has understood it well.